All right, section 3.7. We started this section last time. You can just leave it sit back there. That's fine. I'll get it later. We started this section last time, and we had taken a look at some guidelines. Let me just run through those first before we move back on into where we were. Related rates is the idea of something that's changing over time. And so the rate is still a derivative, but it's a derivative with respect to time. Some steps on how we go about solving a problem like this. Oftentimes, a sketch is helpful. In fact, most of the time it is. Creating an equation relating to that sketch would be our next step. The calculus step occurs sort of in the middle compared to where we did this with optimization. It was occurring towards the end. So you differentiate implicitly, okay? And we did a problem last time and we discovered that the implicit's not quite the same as it was before, but it is similar. So implicitly differentiate with respect to time. That's the part that's different. We substitute in the quantities that we do know, and we solve for the thing that we don't know, which is the remaining rate. And the problem that we had done before was a problem that turned into a triangle problem. And once we drew the sketch, we were able to easily see that it was a triangle kind of problem, right? We talked about the fact that we could also have done something about how the x value at the bottom was changing with respect to time. This problem didn't ask that. But there's several things in terms of a triangle that we could use: sine, cosine, tangent, Pythagorean theorem, stuff like that. All right, we're going to do another example that is the one that we had started last time but didn't finish, was about a spherical balloon. And it was inflated with gas, and we got to the point where we had created the volume equation, 4/3 pi r cubed. We had differentiated it. Over here on the right-hand side, the dv dt is 4 pi r squared dr dt. And we are being told that we want to find dr dt. We had mentioned this at the bottom, right here. Dr dt is what we're looking for. We are told that the radius is 30, and we are told that the dv dt is 800. And I think that gives us everything in the equation that we need in order to solve for the one thing that we don't have. Okay? So dv dt, that one was the 800, so that's going to go on the left. I have 4 and pi, both numbers. The radius, they tell me, is 30, and so that's 30 squared. And then dr dt is exactly what I don't know and what I'm looking for. Everybody good so far? Awesome. All right, so what is 30 squared? 900. What's 900 times 4?
3,600.
Yes, it's 3,600. So we have 3,600 pi dr dt on the right. So what's my last step, so to speak, here? Divide. We're going to divide by that 3,600 pi on both sides. And that's going to leave me with dr dt. Now, you do need to be a little bit careful in your calculator that the 3,600 pi is in parentheses when you do your division. If you just enter it 800, the division sign, 3,600 pi, your calculator is going to think multiply by pi at the very end, not that the division is actually including the pi underneath. So when you're putting this in your calculator, make sure to put some parentheses around that denominator. Okay? What do we get for dr dt? I believe that we were using 4 decimals last time. Does that sound right? Yeah, I think I have 4 decimals from that. Fantastic. 0.0707. Is that what others got as well? Allison said that's what her calculator said. Is that okay, Joseph? You didn't try it. Okay, that's okay. Yeah? Okay, I got it. I got a second, so we're going to have a first and a second, and we're all in favor, right? We need units still. And we talked about last time, the very beautiful thing about this notation is that if you look at the ratio, you can get the units based on the variables in the ratio. What is the variable r's unit? Centimeters. So this is centimeters on top. What is the variable t's unit? Minutes on this one, right? So this would be centimeters per minute. You can write it out in words, you can write it as a ratio, whatever it is you want to sort of make it look like. This is the quantity that we were looking for. Are we good with that one? Okay, the next one's very applicable. This one is too, because we were talking about a balloon. So we've got another one that's going to have a different kind of a shape. Purposely chosen so that you can see how this works with different shapes going on. Oil spills out of a tanker at a rate of 90 gallons per minute. The oil spreads out in a circle, but the circle has a thickness of 1/8 inch. Determine the rate in which the radius of the spill is increasing when the radius reaches 100 feet. Now, there's a lot of weird stuff going on in this one. So let's just talk about looking at it. What do you see as you're looking at it makes you feel like this is a little bit weird? What's different? What makes this particular question awkward?
The height.
What about the height?
It says it's thick, 1/8 inch.
Yeah, we've got a thickness to something. So it's a circle with a thickness. Do you know what shape that's going to be?
Cylinder.
It's really going to look like a cylinder. Okay, so that's something that's a little bit awkward about this one. But it does actually tell you that the height is constant, doesn't it? It's not changing. Kind of like in the problem when we had the triangle where the height that he was off of the water didn't change. So it's really actually not going to be creating a weirdness as much as it felt like, because that one's constant. Okay, what else in this problem is a little bit weird? Or what do you notice about it? Maybe you don't think it's weird, but you notice something here that's maybe different. There's at least two more things, and they are related. How's your thickness measured? In inches. How's your radius measured?
Feet.
In feet. We can't have that in the same problem, right? We've got to either have everything in inches or everything in feet. So we are going to have to reconcile that issue before we actually plug numbers in. We need to be aware of that. There's another issue that's a little bit awkward in terms of units. Gallons. I mean, you guys know that gallons is a volume measurement, right? You don't think gallons of milk, stuff like that. That's fine. But it doesn't really look like something cubed, does it? Certainly not feet or inches, which is the other unit that I'm working with in this problem. So that's a little bit awkward. Okay, so let me show you a few things of what's going on here. Let's draw that diagram with that cylinder that you guys mentioned. Okay, so we've got a cylinder, which is basically, it looks like an oval when you draw it. And then it has, that wasn't good. Not the best cylinder, but it's definitely not the worst one I've ever drawn. Here is my radius out to the edge, so that's R. You guys mentioned that my thickness is 1/8 inch, and I am going to write it in as 1/8 inch, not height, H, because we know this value. It is a constant that never changes. The R value is changing. Now, at some point in time, it's 100, but it's not always 100, so I am writing it as a variable R. Do you guys see why I chose one versus the other? One place I wrote a number, one place I wrote a variable. Okay, great. All right, so this is about the volume of this shape. What's the volume of a cylinder? Do you remember? Volume formula. And it's okay if you don't. Very good. Pi r squared h. Okay, so pi r squared is the area of a circle, right? You probably would have known that one had I asked that directly. And then the height gives you the volume measurement because it's the third dimension. Fabulous. But in this problem, we actually know what the height is. It's a given information, so I can actually change this and put that in. Now, before I do that, we need to take the decision of, do we want to do the problem in inches? And if we do, that 100 feet in inches is going to be a very large number. Or do we want to do that in feet, in which case the 1/8 inch in terms of feet is going to be a very, very small number. And we can do it either way. I'll let you guys pick. You going to do inches? Okay. So our height will be measured in inches, and I can put in the 1/8 right here, and we will move through the problem with that value in. Okay, so for the moment, let's actually write down that eventually we're going to let our R value be 100 feet, and let's figure out how many inches that is. How do I turn feet into inches? Multiply by 12. And I always like writing it this way. I don't know if you guys have seen this or done this in chemistry, but I always do what's called dimensional analysis, where I put the 1 foot on bottom, I put the 12 inches on top, because sometimes when we're looking at a problem, we forget whether it's multiplication or division of values, and this allows us to see the feet canceling out, and so we do very clearly see that it's 100 times 12, which would be 1,200, right? Okay, is everybody good so far? We still have to deal with that weird volume measurement of 900 gallons or whatever it was, right? 90 gallons per minute. So let me actually give you the information that you need in order to make that work. Let's see, where is it? Here it is. I actually had to look this one up when I was creating the notes for this. It tells me in the internet, just so you know, that 1 cubic foot is equal to 7.5 gallons. This is the ratio comparison. So let's take our 90. I'm going to move this 1/8 over here to the other side. All right, so we're going to take that 90 gallons per minute, and I'm going to write it like a fraction. And I want to change gallons, so it's going to go on the bottom, into its corresponding unit that I'm given, which is about feet. So this tells me that 1 gallon is 7.5 feet cubed. Okay, so that turns it into cubic feet, but then we run into a problem. What problem do we run into? Yeah, we've been changing everything into inches, right? And not only is this need to be changed into inches, what did I screw up? Oh, I did. I wrote it backwards, didn't I? I'm sorry. Thank you for noticing. 1 foot cubed is 7.5 gallons. We'll get that in there right. I appreciate that. Thanks, guys. Okay. Really? All right, there it is. Okay, so we had mentioned that we changed everything into inches. So we do need to change this. This measurement will turn everything into cubic feet, but not into inches, and I need to turn it into inches. But there's something else that's going on. It's not just changing feet into inches. Cooper, you said it. It's changing it into cubic inches, right? So that's a little bit different. So let me show you how that works. What I want is I want the cubic feet down here, or feet, 1 foot, if you will, cubed, to cancel out the cubic feet. But I need the inches measurement on top. So you already had told me before that this is 12 inches. But in order to get it into cubic inches, it needs to be cubed, which means the 12 is cubed and the inches is cubed. Are you guys with me? So I actually have to cube that 12 in order to make this happen. All right, so this measurement will cancel out the gallons, and it will cancel out the cubic feet, and I'll be left with cubic inches. So grab a calculator. We need to do the 90, divide it by 7.5, and then it needs to be multiplied by 12 cubed, which is a fairly large number. So the number is going to be bigger than 90 when we're done, right? Hopefully. What do we get when we're done? Did you get it, Cooper? Was it even whole number like that? Yep. Okay, great. What are my units? Someone else tell me what units would be. Good. Inches cubed per minute. So we didn't get to start this problem quite as quickly as the last ones because we had a lot of unit conversions to deal with, right? Now, let me tell you, if I did something on the test where I had a weird conversion like this that you wouldn't know, I'd tell you it. Okay, I'm not going to just ask you to sort of learn something weird. I had to look this one. I don't know this one. I had to look this one up on the internet. So I would give you the conversion if you needed a conversion factor. Okay, but I would assume that you'd know that 12 inches are in a foot. I would not give you that. Okay, let's go back to the calculus part of this. So at this point, taking a look back at our steps of the problem, we have created a picture. We've got an equation relating the relevant quantities, and we've turned all of our relevant quantities into the same unit. That's sort of not written in the steps here, but it is something that has to be done. We're at the point where we're ready to differentiate implicitly with respect to time. So over here's our equation. I'm going to move it to the next slide so I have some more space to work. And we need to take a derivative. So we actually haven't taken a derivative implicitly today, so I want you to take just a minute, write down what you think the derivative is for this, and then we'll check and make sure that everybody's on the same page. Okay, so differentiate this with respect to time. Okay. What did we get on the left? Sounds good. dv dt. What do we get on the right? Okay, there's going to be a 2 pi r. What else will there be? Okay, there's one more thing. We'll still have the 1/8. Yeah, and you can go ahead and make that a 1/4, which I think is what you're saying, Allison, right? So 1/4 pi r dr dt. Why is the 1/8 still there? Some of you did not say it was there, and I have a feeling I know why, but tell me why it should still be there. I mean, it's a constant, but it's a specific kind of constant, right? Like a leading coefficient, it's a constant multiplier is what it's usually called. So when we take a derivative of a constant added or subtracted, that becomes 0 and it's not there anymore. But when the constant is multiplied, it's just part of the problem that's multiplied. So it's a constant multiplier rule. And I think I know all these rates now, don't I? What was dv dt? That's the big number we just found. 20,000, what was it, 736. Okay, I've still got the 1/4. I've got the pi. What's the r value? Almost 1,200. And then I have dr dt. So this is 20,736 on the left. What is 1/4 of 1,200? 300. So I have 300 pi dr dt on the right. And we will divide by 300 pi. To find dr dt. Again, remember to put that 300 pi in parentheses so your calculator doesn't do things out of the order you intended. What do you find for dr dt? 22. Was it even 22? Pretty close. Pretty close. Okay. Inches per what? Per minute. Remember, we look at the units here. R right here was in inches because we turned it into inches. And the time was in minutes. This is inches per minute. If we were working this problem and we were asked to find dv dt, we'd have to make sure that we think about what units are in volume, our volume are in, right? Inches cubed is what we would have in this particular problem. Now, I want to write this down just so that you're aware. Let's say, for instance, you did this problem like this. Looks great. You've got all the right answers. And you look at the back of the book, and they didn't do it in inches. They did it in feet. I don't want you to redo the problem in feet. That would be silly, right? But how could you check to make sure that you have the same answer they really have? Do you have an idea, Fernando? Oh, okay. I'm sorry. Yes, please.
What is 22 inches and, like, what is the inches cube? If the 20,736 was inches cube,
Yeah?
why is not inches cube?
Okay, so right here, this one, oops, let me use a different color to make a minute of it. This problem right here was inches initially, and it was inches cubed per minute, right? This rate is inches, okay? And we had this dr dt will be, your question is why isn't it going to be,
Only inches or not?
this 1/8 right here was in inches. So this is inches, this one's inches. I think this probably was best to probably do. This is inches cubed per minute. So this quantity that's right here in the middle has to be inches per minute in order to have the inches cubed per minute on the right to match what's on the left. So they really do match up. What I tend to do is I tend to not work with any of the units in the middle of the problem and then look at the answer's rate itself. This answer at the this answer at the bottom is dr, which means change in the rate, change in the radius. Radius was in inches over dt, which was time, so the change in time, which was in minutes. So I look at the very end to make my determination. I do know some math professors who will keep the units all the way through the problem so you can see them cancel out, which might be what you want to do, and you can do that. The reason I don't like to do that is because it starts looking really messy because there's so much stuff involved. So that's why I don't do it myself. But you can. If it helps you to figure it out and think through it, you can keep the inches throughout the problem, the units throughout the problem, and watch the units cancel out. Okay?
Thank you.
Okay, so before Fernando had his question, I was asking a question about checking your work. If I did this problem and I got my answer in inches per minute, but I flipped to the back of the book, or I checked with a partner and the partner did theirs in feet, how could we check and make sure that we actually have the same answer? Yeah, this one we could divide by 12. So we could take whatever we have and we could actually figure out, what if I changed it using that dimensional analysis and put it into feet? Well, there's 12 inches in 1 foot. So I could, in essence, multiply my 22 by 1 over 12 to make sure that my answer matches the other answer that somebody else has without everybody really reworking their problems, right? And if you find out it doesn't, then it's probably a conversion change that you missed. Maybe when you did this, you missed cubing something. That's a really common mistake. You did the cubing thing, but you didn't actually cube the 12, or something like that. So it gives you a chance to go back and figure out where it is that you made the error. Okay? Any questions on this one? All righty.